To do that, we need to talk about groupings of independent events. So here is a little lemma. Suppose that I have a collection of sigma fields over a fixed domain, and suppose that I partition them. I take the first 3 sigma fields, and then the next 2, and then the next 1, and then the next 7, and so forth. And I'd like to consider those as groupings. So what I'll do is I'll take the sigma field generated by the first 3 and call that a new sigma field, and then the sigma field generated by the next 2 and call that its own sigma field, and so on down the line. Well, if the original sigma fields, f1 through fn, are all independent from each other, then these grouped sigma fields are also independent from each other. That's what we'd like to prove here, and honestly, the only hard part about this proof is the awful notation of all of the groupings. And so, just to make things easier, I'm going to do it in a special case, but you'll see how the proof works in general. Let's just take a grouping of 2. G1 is the sigma field generated by F1 through Fm, and G2 is the sigma field generated by Fm plus 1 through Fn. Well, we know that sigma fields of independent pi systems are independent. So what we'd like to do is say, hey, this is a pi system and this is a pi system, and therefore their sigma fields are independent because these ones are independent from each other. But that's not true. These are not pi systems. The union of 2 sigma fields is not a pi system. It's not necessarily closed under intersection. But that's okay. All we need to do is turn them into pi systems that still generate the same overall sigma fields G1 and G2. And to do that, well, a pi system is something that's closed under finite intersection, so we just close it under finite intersection. We'll let C1 be the set of all intersections of the form A1 intersect up to AM, where each AI is taken from one of the appropriate FIs between 1 and M. And similarly, C2 will be the set of all things of the form AM plus 1 intersected up to AN, where each AI is taken from the appropriate sigma fields. Those are pi systems by construction. They are evidently closed under finite intersection. They are also independent. Why is that? Well, let's take a C1 in scripty C1 and a C2 in scripty C2. Well, that means that we can write C1 as the intersection A1 up to AM, and we can write C2 as the intersection AM plus 1 up to AN. And therefore, if I want to calculate the probability of C1 intersect C2, that's just the probability of the intersection all the way. Now, those AMs are all taken from these independent sigma fields. And so this whole thing factors as the probability of A1 times the probability of A2 times probability of AM times the probability of AM plus 1 times the probability of AN. But now I can regroup those in the appropriate groupings and say, hey, also F1 up to Fm alone are independent. And so that product of probabilities there is also just the probability of A1 intersected up to AM. And Fm plus 1 through Fn are all independent, and so the events Am plus 1 through An are all independent on their own. And so that product also can be regrouped as the probability of Am plus 1 intersected up to An. And there you have it. That shows us that for any 2 events C1 and C2 in the classes scripty C1 and scripty C2, the product of their intersection is the product of their probabilities. And so that shows that these pi systems are independent. Great. So now I have a lemma from last lecture which tells us that the sigma fields that they generate are independent. But the sigma field generated by C1 is actually all of G1. Why is that? Because, look, if I take any Fi and I take any event in it, AI, I could write that as the intersection of the whole sample space with itself with AI. And that, by definition, is in C1 or C2 if you're taking the AI in the appropriate place later. So C1 contains the union, F1 up to Fm. And C2 contains the union, Fm plus 1 up to Fn. And therefore, the sigma field that it generates contains the sigma field generated by F1 through Fm, which is G1. And similarly, this contains that, but of course is equal to it since the other containment is clear. And so that shows that these two are independent. The exact same proof works in general for larger numbers. It's just a matter of keeping track of all of those indices. Now, a nice corollary of that is that we can group independent random variables. Again, even in this wide general context of having random variables with different state spaces. Suppose that I have a finite collection of independent random variables. Let's say they're indexed by the integers from 1 up to n, and suppose that I have an integer partition of those indices. And suppose that I take any functions of those partitioned collections of spaces. Then the compositions of those functions with the partitioned random variables are still independent. Notationally, that looks like a mess, but this example should make clear exactly what's going on here. In other words, what we're saying is, if I have random variables, say x1 through x5, that are all independent, then so are the classes x1 and x2, x3 and x4, and x5. Those classes of random variables are independent, and in particular, what that means is that if I take these three random variables, some function of x1 and x2, some function of x3 and x4, and some function of x5, then those will also be independent. Why is that? Well, let's do it again in the special case that we had last time. So let's look at partitioning of x1 through xm versus xm plus 1 through xn. Let's let y1 be some function f1 of x1 through xm, and y2 be some function of xm plus 1 through xn. Well, the sigma field generated by y1 is then certainly contained in the sigma field generated by x1 through xm. That is the easy direction of the Doob-Dinkin decomposition theorem. And similarly, the sigma field generated by y2 is contained in the sigma field generated by xm plus 1 up to xn. To be clear, all of this is assuming that the functions involved are measurable functions in the appropriate sense. Measurable with respect to the range sigma field being the Borel sigma field. Well, this is the sigma field generated by the union of the sigma fields generated by each of the x1 through xm. And this is the sigma field generated by the union of the sigma fields xm plus 1 through sigma of xn. And so by the previous lemma, these are independent sigma fields as well. And that means that y1 and y2 are independent. So independence of sigma fields and of random variables is very nice with respect to groupings, as you would hope. Now let's come back to that question from earlier in the lecture about independence versus correlation. Here is an example, which we can now show using the tools we have, of a pair of random variables that are uncorrelated but not independent. And in fact, that's the general situation. It's rare for uncorrelated random variables to be truly independent. Let's take our random variables x and y to have the form x and x times z, where z is a random variable that is independent from x. Now, if I had something like x and y times z here, where x, y, and z were all independent, then the previous lemma would tell us that x and yz are independent. But that's not the situation we're in. X is certainly not independent from x in general. In fact, you can check that it's only independent from itself if it's a constant. In fact, we'll see in a few minutes that generally speaking, these two are not independent from each other. However, if z has expectation 0, then these two will be uncorrelated. That is, provided correlation even makes sense. We need both of the random variables x and y to be L2. So let's assume that x is in L2, and to make things easy, let's assume that z is a bounded random variable, because then z times x is certainly also in L2. Now let's calculate the covariance of x and y in this setting. So that's by definition the expected value of the product minus the product of the expected values. Well, the expected value of xy is the expected value of x squared z. The expected value of y is the expected value of xz. Now x and z are assumed to be independent. We also know that x squared and z are independent from the previous lemma. And since x is in L2, x squared is in L1. So everything squares out, and we can factorize this as the expected value of x squared times the expected value of z minus the expected value of x times the expected value of x times the expected value of z. And hey, our assumption here was that the expected value of z is 0, which means that this is 0. So those are indeed uncorrelated random variables. But are they independent? Well, let's take this a little bit further. Let's try to calculate the expected value of x to the n, y to the m for some powers n and m. Well, we don't know that we can actually define that. X to the n times y to the m may not be an L1 random variable. So we'll make some assumptions that will allow all the calculations to be justified here in a second. But let's just do this the way we know it will have to work if everything is well defined. This is just the expected value of x to the n times x to the m, z to the m, which we can recombine as the expected value of x to the n plus m, z to the m. And now, if x to the n plus m happens to be in L1, and z to the m is in L1 because it's bounded, then we know that this will factor as the expected value of x to the n plus m times the expected value of z to the m. Now on the other hand, if I take the expected value of x to the n times the expected value of y to the m, doing the same calculation, what we'll find is that that's equal to the expected value of x to the n times the expected value of x to the m times the expected value of z to the m. Again, that will be valid provided that both x to the n and x to the m are in L1. But as you can guess, these two things are typically not going to be equal. Now we got that they were equal in the special case up above where n and m are both 1 because of the assumption that z had expected value 0. So, if that term happens to be 0, then sure, these are going to be equal. But they're not really structurally equal because of this factorization property. Expected value of x to the n plus m typically will not equal expected value of x to the n times expected value of x to the m. That sort of looks like x being independent from itself, which, as we've noted, really only holds when x is a constant. In fact, we can show that this doesn't work in lots of situations. We just need to make sure these conditions are met, and we can do that by, for example, taking x to be a standard normal random variable. Standard normal random variables have finite moments of all orders, as we've previously calculated. And as for z, well, we have lots of choices, but we could, for example, take z to be a Rademacher random variable, which is a symmetric version of a Bernoulli. That is, its law could be 1/2 a point mass at 1 plus 1/2 a point mass at -1. Then it does have expectation 0, and it is bounded by 1. Now let's just check to see what happens with these equations here. Let's do it with n and m both 2. Then the expected value of x to the 2 plus 2 is the fourth moment of a Gaussian, and we've seen what that is before. It's equal to 4 minus 1 double factorial, or 3 times 1, which is 3. On the other hand, if I take the expected value of x squared times itself, for a standard normal, that's just 1. And so, indeed, these two do not agree. But with m equal to 2 here, the expected value of z squared here is just 1, as you can check. And so this is an example, with x being a standard normal and z being a Rademacher. X and xz are not independent, even though they are uncorrelated. Let's emphasize this point one more time. How did this show that these two are not independent? Well, we have a theorem which tells us one of many equivalent formulations of independence. But one of those characterizations was factorization of expected values when the functions involved are appropriately integrable. If x and y are independent, then x to the n and y to the m are independent by the previous slide. And if x to the n and y to the m are both L1, then those random variables being independent implies that the expected value of their product is the product of their expected values. That failure here shows that these two are not independent. Now, if